Hello. So I'm Daichi Mochihashi. So I will talk about directly learning words from acoustic futuristic observations. Actually, this is complementary to the Takahiro's work and Mirko's work just explained. So, this one. Yes. As you know, so this is my nested Pitman language model that transduces from the string of words. So, extending this model, so Graham Newbeck proposed the lattice language models that transduces lattice to words because even if speech recognition input string is not always certain. So this lattice is even if the input is ambiguous, WFST representation allows word segmentation over phonetic lattices. So this is phone lattices, and this is word segmentation. So this Chinese pinyin Chinese may not be correct, but you can see the idea. So in order to this lattice is based on obtained from acoustic HMM. So the natural extension is to begin not from beginning from the HMM to begin from acoustic data itself. That is a very ambitious idea. So this is the actual example of discrete MFCC sequences. So what we want to learn is from this kind of acoustic data to induce that kind of unsupervised phoneme that actually represent I'm a boy or hi hi guys. So this is a completely unsupervised problem to induce the phone and possibly words that is equivalent to the sequence of unsupervised phones only from the acoustic data. So this, and just as the Takahiro's figures, this is only observation. So this is a hidden HM stated sequence is hidden, and phones are hidden, and words are hidden. So, but however, so there is no free lunch. So actually, so we can inject structured priors. For example, so speech recognition, we can assume the left to right HMM for each font, and in this level, so on the higher levels, we can assume the Pitman process to that has a that has a heavy tails for zip-like distributions. So this kind of structured priors will allow us to learn the words only from the acoustic observations. So technically, the general strategy is to compose many HBSTs repeatedly. So for example, so there is a WFST from that converts the state, the acoustic feature in this state, and the upper levels there is another WFST that converts state to the phone, and finally there is a WFST of nested Pitman language model that converts phone to words. So we can connect these WFSTs. Actually, there is not 3. Actually, there is 5 or 6 WFST to find a connection from the lowest level acoustic HMM to the highest level words in the WFST implementation. So this is actual example. So this is actual observation of discretized MFCC sequences. Oh. this is vertically rotated. So really, you can see this one is actually relates to this one. So this is observation HMM. So this is a monophone. Actually, surprising. This is a monophone WFST from left to right structure. So phone simplicity, we only assume the 4 types of unsupervised phones. So there is a phone 1, phone 2, phone 3, and phone 4. So connecting these two WFSTs, this is a composed HMM WFST. So this is actually extremely simple because we only assume 4 types of unsupervised phones and six frames for presentation. But however, so you can see here the frames are 6. There might be some. So each phone consumes 3 frames left to right. So there is some possibility. So there is 2 phones, 3 frames and 3 frames. So this arc is a possibility for the different phones. So we generally this is input FSTs. So our next task is to combine this input FST for acoustic sequences with the language models. So combining this FST with the language model. Really, I confirmed before the presentation that this is clear. Really. So
this is good.
Really.
Very complicated.
Yeah. Yes. So this is a composite FST with extremely large number of arcs. So there is many bypasses like this one through existing words, and so we sample from this complicated FST. So implementation is actually based on Professor Ambacha's lattice word segmentation program. So I put a very large effort to understand his program. So Padamon's program. So this is actually the center of the modification acoustic HMM to create an input FST. But however, this is not only the modification. There are many patches that are required to run this program. So actually, it worked. So actually, this figure is much larger. So let's name the only phone, unsupervised phone as A, B, C, and D. So this is the result. So we only provided this data, this sequences unsupervised, this sequences MMCC sequences. This data is converted to the 3 words: B, D and B, and the B or D or B is actually corresponds to some HMM for acoustic features. So the lower level, this is the lowest level HMM states 4, 5, 6, 7. So this is the result of the sampling. So using this HMM states, we can update HMM and update the language models and iterate over. So this is a caveat. So words like the A, B, or B, C using unsupervised phones, there are no clue to connect with no knowledge for language. So Takahiro's work and Mirko's work will have, they are complementary to this model. So because knowing some relationship between sound and spelling will connect the knowledge of unsupervised result with our knowledge. So that is our next theme to complete the finally unsupervised speech recognition. So time is coming. So I just omit stochastic planning works. So this is a conclusion. So I showed that we can actually induce words only directly from the acoustic observations. So using the previous presidential campaigns of USA, I would like to say to yes, we can. So connection to other knowledge or dictionary or grapheme phoneme is necessary and useful for future research. So more complex acoustic models or triphones and neural HMMs will help much. So, and because I am a natural language processing people rather than speech recognition, so I will say thanks to the great opportunity here for the members and the organizers. That's all.